Up to this point, you used equilibrium to understand pH, acid strength, buffers, and titrations. In this final video, we're going to apply those same ideas to solubility using the solubility product constant, or Ksp. You'll learn how to determine if a compound will dissolve, how to calculate molar solubility, how to predict when a precipitate will form, and how common ion effect shifts equilibrium. This is the last piece of the puzzle, so let's finish strong. So consider the following sample here. All right, I have barium sulfate, which is a solid. And if I try to dissolve this, I should get barium 2 plus aqueous and a sulfate ion, 2 negative aqueous. The equilibrium constant describes how soluble the solid is in water. We'll refer to this constant as the solubility constant, or Ksp. Ksp is equal to the concentration of the barium raised to a power times sulfate raised to a power. This power will be the coefficient within the equation itself. Now for barium sulfate, we have a Ksp of 1.1 times 10 to the negative 10th. That's a very small amount of solid that will dissolve in water. So the larger the value of the Ksp, the more soluble the salt is in water. We're going to say that solubility describes either the grams of solute per liter or the moles of solute per liter. Okay, in our first problem, we're going to determine the solubility product constant for barium carbonate. So barium carbonate solid we know that Ksp is related to how soluble it is. So we know that Ksp is going to equal both of those be raised to the first power. Okay, so we have 1.4 times 10 to the negative 3 grams per 100 milliliters. We got to convert this into moles per liter. So for barium carbonate, has a molar mass of 197.3 grams. And I know that there's 1,000 milliliters per 1 liter. All right, so these grams cancel, these milliliters cancel. So this gives me 7.1 times 10 to the negative 5 molar BaCO3. So that means I have 7.1 times 10 to the negative 5 moles of barium. I also have 7.1 times 10 to the negative 5 moles of carbonate. So if I multiply this out, I will get my Ksp. So I'm going to square 7.1 times 10 to the negative 5. I get 5.0 times 10 to the negative 9. Now, Ksp is unitless, so you don't have to worry with units here. So that's the answer to the first question. Okay, in problem number 2, the solubility product constant for lead fluoride, that'd be lead 2 fluoride, by the way, is 3.2 times 10 to the negative 8. Calculate the lead 2 ion concentration and the fluoride concentration in a saturated solution of this solute. So I know that we're working with PbF2. We know the Ksp is 3.2 times 10 to the negative 8. So Ksp is equal to the Pb2 plus concentration times, I have two F's here. I have to put a square there because there's two of those. All right, so I'm going to say that 3.2 times 10 to the negative 8. Okay, I'm going to let X represent lead. I'm going to say 2X because I have two fluorides, and I have to square it. So it'll be 3.2 times 10 to the negative 8. All right, 2 squared is 4, so it'll be 4x to the third power. Divide both sides by 4. I would get 8 times 10 to the negative 9 equals x cubed. So x will be equal to the cube root of 8 times 10 to the negative 9. So x is equal to 0.002, or I can say 2 times 10 to the negative third power. So the Pb2 plus concentration will be equal to 2 times 10 to the negative third molar. The F negative concentration will be 2 times this, or 4 times 10 to the negative third molar, because I have two F's in the equation here. And when it dissolves, it dissociates into two F negatives. So that's the answer. Okay, this next problem here, you're given the Ksp. The Ksp is 1.1 times 10 to the negative 12. So I know the Ksp is going to equal, I have 2 silvers squared times my chromate like this. So I would say 1.1 times 10 to the negative 12 equals 2x squared times x. All right, I'm giving an initial, I have 2 milliliters of a 0.5 silver nitrate solution. So we need to calculate the amount of silver that's in this. So here on the side, I'm going to say 0.5 moles of silver ions per liter. And I have 2 milliliters, so 2 milliliters will be 0.002 liters. So that would give me 0.001 moles of Ag+. That is the actual amount, okay? So we'll write it out. This is the actual amount of silver. Therefore, I'm not going to be multiplying it times 2 here. Okay, since it's the actual amount. So it would be 1.1 times 10 to the negative 12 equals 0.001 squared times an unknown amount of chromate. Let's solve for the amount of chromate here. Okay, so X is equal to 1.1 times 10 to the negative 12 divided by 0.001 squared. So X is going to equal 1.1 times 10 to the negative 6 moles of chromate. So this is the amount that will be required to precipitate silver chromate. So in problem 4, if the Ksp of silver chloride is 1.56 times 10 to the negative 10, determine the solubility of silver chloride in grams per liter. So Ksp is going to equal the concentration of silver ions times the concentration of chloride ions. So it would be 1.56 times 10 to the negative 10 equals X times X. So X will be equal to the square root of 1.56 times 10 to the negative 10. So X is going to equal 1.25 times 10 to the negative 5 molar. So we have 1.25 times 10 to the negative 5 molar. All right, let's convert that into grams. So 1 mole of silver chloride. Silver is 107.9. Chlorine is 35.45. If I add those together, I would get 143.35. Okay, so now we can count some of moles. This gives us grams per liter. That's what we're looking for. So this is equal to 0.00179 grams. Or I could say 1.79 times 10 to the negative third grams per liter. That's our answer. Will precipitation occur when 50 milliliters of a 3.00 times 10 to the negative 2 molar lead-2 nitrate solution is added to 50 milliliters with a 2.00 times 10 to the negative 3 molar KCl solution? The Ksp for lead-2 chloride is 1.62 times 10 to the negative 5. I can pretty much guarantee you'll probably have a question like this on your test. So you need to think in terms of Q here. So Q is going to equal to, same thing, the PV2 plus concentration times the 2Cl negative square concentration. And you know that Ksp for the lead-2 chloride is going to be equal to 1.62 times 10 to the negative 5. First thing let's do, let's find our moles of lead-2. So I have a 3.00 times 10 to the negative 2 moles of lead-2 per liter. And I have 50 milliliters of stuff, so that would be times 0.050 liters. That will give me 0.0015 moles of lead 2. Let's do the same thing for the chloride. I have 2.00 times 10 to the negative third moles of chloride per liter. Have 50 milliliters of that also, 0.050 liters. I'll multiply this out, I get 1 times 10 to the negative 4 moles of chloride. Let's convert this into concentration. So my PB concentration is going to be equal to 0.0015, that's moles, divided by the total volume. I have 50 plus 50. Both of those are liters. That will give me 0.015 molar lead 2. Same thing with the chloride. I have 1 times 10 to the negative 4 moles chloride divided by 100 milliliters. So that's going to give me 0.001 molar chloride. Okay, let's solve for Q. So Q is going to equal 0.015 times 0.001 squared. I'm taking this equation here. So Q is going to equal 1.5 times 10 to the negative 8. All right, let's compare that to the Ksp up here. That is less than 1.62 times 10 to the negative 5. So my answer is no precip forms, because my Q value was smaller than my Ksp, so therefore no precipitate occurs. Okay, in problem 6, we're going to be mixing two solutions again, and we want to see if a precipitate will form. Okay, I know my Ksp for lead 2 sulfate is equal to 1.06 times 10 to the negative 8. So I'm going to be solving for Q, so Q is going to equal my concentration of lead 2 times my concentration of sulfate. Okay, let's find the concentration of lead. So I have 0.1 moles of lead per liter. Okay, times I have 10 milliliters, that'd be 0.01 liters. That would give me 0.001 moles of lead, 2 plus. Same thing for sulfate. I would have 0.0010 moles sulfate per liter. And also 10 milliliters times 0.01 liters. When I multiply this, I should get 1 times 10 to the negative 5 moles of sulfate. Now let's get our actual concentrations. So I have 0.001 moles of PV divided by my total volume. So that'd be 10 plus 10, that's 20, so it'd be 0.02 liters. So that would give me a 0.05 molar concentration of PV2 plus. For my sulfate, 1 times 10 to the negative 5 moles of sulfate over 10 plus 10, which is 20 milliliters, or 0.02 liters. All right, so that'll give me 5 times 10 to the negative 4th molar sulfate. So let's take this equation here and let's substitute in. So Q is equal to the lead concentration, which is 0.05 to the first power. The sulfate concentration is 5 times 10 to the negative 4th. So I multiply this out, I get 2.5 times 10 to the negative 5th. Okay, so 2.5 times 10 to the negative 5th is greater than the Ksp value of 1.06 times 10 to the negative 8. So the answer is yes, precip occurs. Okay, problem number 7. Calculate the molar solubility of calcium fluoride in a solution that contains 0.010 molar calcium nitrate with a Ksp for calcium fluoride of 3.9 times 10 to the negative 11. Okay, this is called the common ion effect. Because I have calcium here and calcium here. Now we know the Ksp is going to be 3.9 times 10 to the negative 11. So let's write out our equation here. So we have calcium fluoride, which is a solid, producing calcium 2 plus and 2 fluorides. Let's do an ice table here. Since this is a solid, we can ignore it. All right, my initial calcium will be 0.010. I have no fluoride. We're going to be gaining X, gaining 2X. So this is going to be 0.010 plus X and 2X. All right, this X is very small because of my 10 to the negative 11 power. There's many powers of 10 between them, so I can basically ignore this. So I can complete my Ksp now. So Ksp 3.9 times 10 to the negative 11. That's going to equal my calcium, which is 0.010. times 2x squared for my fluoride. So I would have 3.9 times 10 to the negative 11 is equal to 0.01 times 4x squared. Divide both sides by the 0.01. So we get 3.9 times 10 to the negative 9 equals 4x squared. Divide both sides by 4. So x squared is 9.75 times 10 to the negative 10. Take the square root of both sides. So x is going to equal 3.12 times 10 to the negative 5. So for my answer, I would say 3.12 times 10 to the negative 5 molar calcium fluoride. Okay, on problem 8, we're doing basically the same problem as problem 7, except with our common ion this time will be the fluoride ion. So still our Ksp is 3.9 times 10 to the negative 11. Again, we're going to do our ice table. This is solid, so we can't ignore it. All right, initially I have no calcium, but I have 0.01 moles of fluoride. This will be plus x, be plus 2x. Okay, again, this x is very small. If I have a Ksp of negative 11 there, so we're going to basically ignore it. So we're going to say the Ksp, which is 3.9 times 10 to the negative 11, is going to equal my calcium times my fluoride. That'd be 0.01 squared. All right, so x is going to be 3.9 times 10 to the negative 11 divided by 0.01 squared. So x is going to equal 3.9 times 10 to the negative 7th. So I can say then 3.9 times 10 to the negative 7th molar calcium fluoride is my answer. Okay, so which of the following salts will be substantially more soluble in an acidic solution than in pure water? All right, so in general, if a compound contains basic ions of the ion of a weak acid, then its solubility will increase. As the solution becomes more acidic. So when I look at negative ions or anions of weak acids, so weak acid anions, I think of things like carbonate, phosphate. Just think of all your weak acids. Okay, those are some examples. So, which of these will be more soluble? You gotta look at the CO3. CO3, the acid was carbonic acid, a very weak acid. Therefore, this is a basic anion. So, yes, this one will dissolve better in an acid solution. All right, HI is a very strong acid. So therefore, its anion is a very, very, very weak base. So no. Hydrogen cyanide is a very weak acid. So therefore, it will become more soluble in an acidic solution. Phosphoric acid is a very weak acid. Therefore, it has a strong basic anion, which will make it more soluble in an acidic solution. So my answers will be A, C, and D. If you can use Ksp and Qsp to predict solubility and precipitation, you completed the full picture of equilibrium chemistry. Thanks for sticking with the series. I'll see you in the next topic. Please consider sharing this series of videos with someone else taking chemistry. Please like and subscribe. It really helps the channel grow. Thank you for watching. Goodbye.